in last week we have the Ambedkar sir has given a very nice lecture on oscillations, and he has also explained the different types of the oscillations. So today we have amongst us Dr. Gorakshnath Gote. So before I introduce, I welcome you all the students, all the teachers also, and I thank Gurpade ma'am for starting the streaming of Zoom meeting. So let me introduce today's speaker. We have amongst us Dr. Gorakshnath Gote. Uh, Sir has qualified the PhD and CET exam, and Sir is currently serving as Associate Professor at SP College, Pune. Sir has earned his doctorate from Department of Physics, Savitribai Phule Pune University. He has worked in association with National Chemical Laboratory, Pune, with the research topic Development of Nanomaterials for Electron Gun using Field Emission Microscopy. Sir has for his work, this work has reflects his expertise in advanced materials and applied physics. Dr. Gote has published several research papers in peer-reviewed journals, contributing to the growing body of knowledge in nanoscience electron emission technologies. Renowned as an inspiring and dedicated teacher, Dr. Gote has an exceptional command over subjects such as quantum mechanics, classical mechanics, electrodynamics, statistical mechanics, and mathematical methods in physics. His clarity of thought and engaging in, teaching style have made him a respected mentor among students and colleagues alike. Beyond classroom teaching, Dr. Gote has been invited to deliver the lectures in PhD coursework programs at multiple centers, where his insights have guided and motivated aspiring researchers. His academic rigor, pedagogical excellence, and commitment to nurturing scientific curiosity make him a distinguished figure in the field of physics education and research. So, I welcome Dr. Gote sir for today's session, and over to you, sir. Thank you very much.
Yes, sir. Yes, sir. Thank you, sir, for my kind introductions. Welcome you all and good evening. In the fourth session, I think this is the fourth session of NGPE 2026 online bootcamp. I must say thank to Rekha Gurpade madam, Bharat Kalmude sir, and Shashikant Shinde sir for organizing such a nice sessions for student benefits. Students, here I have been just selected the some problems from last year NGPE question papers of the quantum mechanics subject. I will start from the very basic problems. Here is the first problem is de Broglie wavelength of the electron. Now we know what is a de Broglie wavelength. Lambda equal to h upon simply a momentum, right? It is mass into velocity, right? Now, see, as this electron moving with this much of the velocity, so this is a relativistic problem. So we should take this relativistic mass. So m equal to m naught rest mass square root of 1 minus p square upon c square, right? Also velocity is given v equal to c upon root 2. So substitute that velocity here, okay, and in this equation, and just simplify the this equation, de Broglie wavelength. So we get m equal to m naught square root 1 minus, instead of this we substitute this c upon square root of 2. So we get c square 2 c square, right? So this c square get cancelled and we get m naught upon 1 upon root 2, right? So, or we can write here m naught root 2 only. Now substitute that in this equation, lambda equal to h upon m, and velocity is given c upon root 2, right? And this mass is m naught root 2 into c upon root 2. So this root 2 get cancelled. So simply we get h upon m naught c. And this is called the Compton wavelength. Okay. So this question is asked 2 times in January 2013 and January 2015. De Broglie wavelength, Compton wavelength. Now let us move the one more relativistic problem. Here the show that de Broglie wavelength of an electron of mass m0 rest mass is accelerated by this with the high potential phi, then show that this is a de Broglie wavelength. Now, in this case, again, we have to use a very basic formula, lambda equal to h upon p, momentum. Now, we know in case of a relativistic case, relativistic relation of energy E equal to square root of p c square m naught c square bracket square, right? And also we have the one more relation, E equal to rest mass energy plus some kinetic energy. Okay, so equate these two equations and simplify for the momentum. So squaring this equation, okay, suppose say this equation number 1 and 2, squaring equation 1, what we get? We get p square c square plus m naught c square bracket square equal to, just expand this, a plus b bracket square. So here we get m naught c square bracket square plus twice of m naught c square k plus k square, right? So here this term get cancelled. Okay. So simplify for p. So we get p square is equal to, it is, so divide this c square to the right side, we get twice m naught k, right, plus k square upon c square. Okay, so we get p equal to square root of 2 m naught k plus k square upon c square. Okay, so substitute that in this relation. So what we get? Lambda equal to h upon whole square root of k square c square plus twice m naught k, right? So from this, take this term common, right? Because here we require 1. So take this term common. So what we get? Lambda equal to h upon square root of 2 m naught k 1 plus here k only, and here 2 m naught c square, right? Now, what is k? K is a kinetic energy. So we know that how we define the kinetic energy of accelerated electron. Kinetic energy is EV. So simply substitute that here. Okay, so we will get this relation. Okay, instead of k, substitute E into V, right? So we will get this relation. Okay, so this question is asked for 10 marks. Now, so after this, let's go to the wave function. What is the wave function in quantum mechanics? Okay. Now we know that as such wave functions does not have any physical significance, but mod of psi square has some physical significance, right? So it gives the probability of finding the particle in a particular region. Okay, but now see in quantum mechanics, every function, okay, or wave function is not acceptable. It should fulfill some conditions. Okay, so before uh, seeing the option of this, let us see what is the requirement of wave function. What is acceptable wave function in quantum mechanics? Requirement of wave function. Okay, so first condition is wave function should be a continuous one. wave function must be continuous. See, what is meaning of this? Continuous means if that is any function, okay, that means its value should be defined everywhere. Or we can say in another way, if you approach to any function at a particular point from the left side, and also if you approach from the right side, so we should get a single value, right? Something f of a, right? So these are first requirement. Wave function should be a continuous one. Okay, but now see, in this case here, this function is not a continuous one. Okay, if you approach from the left side, okay, if you approach from the left side, we will get this value, and if you approach from the right side, okay, here we get a different value. Okay, so this function is discontinuous, right? So this option is wrong. Second condition, wave function must be a single valued. Single valued. So what is the meaning of this single valued? Means what? For example, let us say, suppose we have some functions like this, suppose like this, okay, and for a particular value of x equal to x naught, if you give the two values, okay, this function gives the two values for a single x is equal to x naught, there are two values, so these are double valued function. Such functions are not acceptable in quantum mechanics, right? So if you observe in this graph, for suppose say at a particular point, say x is equal to a, we get this function will give this value, and for this graph this will give this value. Okay, so you again a double valued function. So again, this is not an acceptable function, right? Okay, and third condition, wave function should be a differentiable everywhere, continuous and differentiable. That means differentiable. Okay, now see, in this case, so how to know given function is differentiable or not? Okay, even though some functions are continuous but not differentiable. For example, if you take the graph of mod x, okay, so this function is continuous at the origin, but it is not differentiable here. Okay, okay, so simple trick, we can say how to know from the graph a given function is differentiable or not. Okay, if given function having a like this hump like shape, so this function is not differentiable there, right? So if you observe here, there is something hump like this. Okay, so because of this function not differentiable there. Okay, so again, this wave function is not acceptable in quantum mechanics. Okay, so only option is this one. Okay, so it satisfies all the condition. It is a continuous everywhere. Okay, it is single valued. For given x is equal to x naught, it gives a single value only, right? Even though at a particular value it gives the same value, that means it is a what we can say, it is not a multi-valued function. Okay, for a given x, some angle is there, we get this value. For another angle, we get the same value. Okay, so it is a many to one function, so such functions are acceptable. Okay, then it is differentiable also. Okay, so this is the answer, right? Okay, now, so it is asked for 5 marks. What is acceptable wave function? Let us see one more example on this. This question is asked in January 2019. Some functions are given, so we have to find the which function quantum mechanically acceptable wave function, which function is acceptable quantum mechanically. So for that, we should know what is a graph of these functions. Okay, first of all, let us see the graph of this function f of x equal to 1 upon x minus x naught. Okay, now this function is goes to infinity at x is equal to x naught, right? That means suppose at a particular point, say x is equal to x naught, okay, here this function is infinite there. Okay, if if x is greater than x naught. Okay, so graph will be like this for x greater than x naught, and if x is less than x naught. Okay, so in that case, we have to draw the graph in this quadrant. Okay, So here for x is equal to 0, we get 1 upon something minus x naught, right? So again, in this graph, there is a discontinuity here. Okay, so this function is not acceptable. Now, let us move to this function now. So first of all, we should know what is the nature of this graph. Okay, mod x. Now, mod x, we know mod x means what? Is equal to plus x for x greater than 0, and mod x is equal to minus x for x is less than 0, right? So we have two functions. F of x equal to exponential of, if we choose this one, mod x is equal to positive, so we get minus x upon x naught, right? So if you plot the graph of this exponential function, right, so we get a graph of like this for x greater than 0, like this. And for the x negative, so what we get? F of x is equal to, it is a negative, so this negative become positive, right? So it is an exponential of x upon x naught, right? So this graph is something like this. Okay, so again, because of this sum, this function is not differentiable there, right? Now, same way, on the same graph, we could plot the graph of this function also, exponential. As x tends to infinity, it goes to infinity, right? This is a graph of exp of exponential of plus x, right? So again, this function goes to infinity, right? As x tends to infinity, right? So this wave function is not acceptable in this region, okay? It is acceptable in this region only. Which one? From minus infinity to 0, okay? It goes to 0, okay? But for in this region, okay, this wave function is not acceptable. But now, what is the graph of this function? Okay, graph of this function is like this. For x equal to 0, what do we get? 1, right? And if x tends to plus infinity, again it tends to 0, right? That means e raised to minus infinity, it tends to 0, right? So graph is something like this, okay? And for x tends to minus infinity, so here square of the minus infinity is again infinity, and there's a minus sign, so it is again minus infinity, okay? So e raised to minus infinity tends to 0. This function is normalizable, okay? It is continuous, differentiable, okay? You fulfill all the requirements of wave function, so this function is the acceptable wave function in quantum mechanics, right? Now, so after studying the requirement of wave function, let us move some problems. Now, this question is asked in January 2000, last year. Knowing the ground state wave function for hydrogen atom, ground state wave function is given. We have to find expectation value of 1 upon r for 1s. That means for ground state, right? Now, so we know what is the formula for the expectation value. 1 upon r, it is from see, now this is a hydrogen atom. So what is the limit of this? This is a three-dimensional problem. R vary from 0 to infinity, right? Theta vary from 0 to pi, and phi vary from 0 to 2 pi, right? And mod psi square into d tau, a small volume element, right? Now, see here, as if we consider this a whole sphere, okay, as a solid sphere. In that case, we know that what is a volume element? What is volume element? It is simply r square sine theta, d theta, and d phi, right? So after evaluating this one, theta from 0 to pi and phi from 0 to 2 pi, we get a 4 pi r square. Sorry, dr should be there. Dr. So this volume element for a sphere, we should take this volume element 4 pi r square dr. So substitute that in this relation. Okay, so simply we have to evaluate the integral of r only. Okay, so from 0 to infinity, right? Then it is a real function, right? It is a real function. So it is 1 upon square root of pi a naught cube, right? E raised to minus r upon a naught, right? This is a psi star. Then 1 upon r into again 1 upon square root of pi a naught cube e raised to minus r upon a naught. Okay, and then volume element. It is a r square, 4 pi r square dr, right? So if you take this constant out of the integral, okay, so what we get, and 1 r get cancelled. Okay, this r, 1 r get cancelled. So you can write expectation value equal to 1 upon pi a naught cube. Here a naught is a Bohr radius, and it is a 4 pi again, this constant. Okay, and integration from 0 to infinity e raised to, the base is same, it is a minus 2r upon a naught into dr, right? Now see, this is a very standard integral. If we have such type of integral, there is some standard formula in terms of gamma functions. E raised to plus infinity, suppose x raised to n, e raised to minus alpha something constant x dx. Then there is a gamma of n plus 1 upon alpha coefficient of this into n plus 1, right? So more oftenly we require this. Also we require one more formula. Most of so in this problem we do not require this one, but you should know from 0 to infinity x raised to n e raised to minus alpha x square into dx. In that case, we have to write 1/2 gamma of n plus 1 divided by 2 alpha raised to n plus 1 divided by 2. So more frequently we require these two formulas, okay, to solve such type of integral. Now, so as there is power of r is 1, so we should use this formula, right? Now, so our integral is expectation value of r equal to, again here pi get cancelled, right? So we can write 4 upon 4 a naught cube and integration of this. So what is the formula? Gamma of, okay, gamma of power. So what is the power of r here? R, we can take r raised to 0. So it's 0 only, right? Okay. Sorry. No. There is one r is there. Sorry, this one r is there. 4 pi were taken out of the integral, one r is there, right? R is there. So power of r is 1, right? 1. So we should write, instead of n, we should write here 1 plus 1, 2, gamma of 2, divide by alpha. Alpha means what? Coefficient of r. So 2 upon a naught. It is 2 upon a naught square of that, right? Okay. Now let me comment what is the definition of gamma here. Okay. Gamma is defined like this. If gamma of n is equal to n minus 1 factorial. Okay. Now, so expectation value of r 4 a naught cube, then what is the gamma of 2? It's a 1 factorial, right? 2 minus 1, 1 factorial. So it is 1 only. And square of 2 is 4. And again, square of a naught is a naught square. So this 4 get cancelled, a square get cancelled. So we get 1 upon a naught only, right? So answer is D here. Okay, answer is D. So let us move to the next problem. Anybody having any query, you can ask in between the lecture also. Now, see, consider a particle of mass m confined in region this and potential wave functions given, normalized wave functions are there. Okay, and
Some part is missing.
yes, sir. Hello.
Some part of the problem is missing,
Hasan,
sir.
which one?
The same, the problem which you are already.
A previous problem. This one. Hello, sir.
Take the
Shashi, sir.
problem, but
Ha.
some part is.
Okay, 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 okay. Okay, sir. So this is the next problem. Consider a quantum particle of mass m confined in the region of 0 to L in one-dimensional potential well if phi naught of x and phi 1 of x are normalized eigenfunctions of ground state and first excited states respectively. If wave function of the particle at t equal to 0 is given this. Now, see, in this problem, there are two words are there, eigenfunctions and wave functions. Now see, what is the difference between these? Wave function, let me revise first some basic theory before solving this problem. Wave function is a linear combination of the eigenfunction. So here, this is eigenfunction and this is a wave function. So here, wave function is given in terms of eigenfunctions, right? So here we can write. Before that, let me revise the infinite potential well problem. Okay, in shortly, let me infinite potential well. I'm not going to solve this. We will be get this derivation in its standard quantum mechanics books. Infinite potential well, eigenfunctions and eigenvalues. Phi n of x equal to square root of 2 upon a if the width of well is from 0 to a into sine of n pi a into x. This is the eigenfunction. And eigenvalue en equal to h cross square pi square to m l square into n square, right? Or so here en is start from 1, not from 0, 1, 2, 3, 4, and so on, right? So also en we can write in terms of a ground state energy n equal to 1 like this, E1 into n square, right? So knowing this one, want to find the average value or expectation value. Now here I'm just going to write a direct formula of how to find out the expectation value of or average value of energy equal to summation n is start from 0 to infinity, then mod of Cn square into En. This is a formula for to find out the average value of energy. Okay. Now, so to find out the average value of energy, we should know what is the coefficient, these coefficients, right? And what is the corresponding energy. So observe on this problem. Okay, let me rewrite that. Psi of x equal to 1 upon root 2 phi naught of x plus 1 upon root 2 phi 1 of x, right? So as you compare this equation with C1 or say C0 phi0 of x plus C1 phi1 of x. So we'll get these coefficients, right? So by comparing this one, we will get C0 is what? 1 upon root 2, right? And C1 is 1 upon root 2 again. Okay. So knowing the coefficient, we can easily find out the average value, right? So average value of energy equal to, so two states are given, ground state and first excited state. So we should write here mod of C square E naught plus mod of C1 square E1, right? So simply substitute that values and see what we get. So square of this, it is 1 half E naught, right? Plus 1 half uh, square of the C1, right? Into E1, right? E1. But now we know that En can be written in terms of ground state energy, right? E0 into n square. So here n is equal to 1. So we can write En is equal to 1 square. It is a sorry, 1 minute. N should be 2 here for first excited states. N is equal to 2. Okay, so 2 square. So it is a 4 E naught, right? So we can write here expectation value of energy H equal to 1 half E naught plus 1 half E1 is 4 E naught, right? So expectation value of energy equal to, we can write is of 4 plus 1 5 upon 2 E naught, right? But what is E naught? What is the ground state energy of hydrogen atom? It is h cross square pi square 2m into L square, right? So here we get answer the 5 upon 4 h cross square pi square upon m L square, right? So this is the expectation value, right? So this problem is asked for, I think, for 10 marks. Find the expectation value of energy, right? Now, let us see the one more problem to find the expectation value of energy. Okay. Now, this problem is what we can say somewhat lengthy problem actually. Okay, so this problem is asked for 10 marks. Now, so this is the wave function, right? See, again, let me read the problem. A particle in a finite potential well, P of x is equal to 0 in between this region, 0 to A, and it is 0 outside the well. So it is an infinite potential well problem. In this state, is in the state represented by the wave function this. Okay, so this type of the wave function is there inside the infinite potential well. Is a wave function. Okay, so we have to split up this wave function in terms of eigenfunction of a particle in infinite potential well. That is we know what is the eigenfunctions of particle in infinite potential well, right? A sine and pi a into x. So you see here width of the potential well, here I have taken a now, right? And corresponding eigenvalues, this is h cross square pi square 2m a square into n square, right? Now anyhow we have to express this wave function in terms of this. Okay, so for that we have to use a formula for sine t theta equal to 3 sine theta minus 4 sine cube theta. Okay. So simplify this equation for sine cube because we have given sine cube. We want to express this sine cube in terms of sine only. So it is a sine cube theta equal to, take this term to the left side and this term to the right side. So what we get? We get the 3 upon 4 sine theta minus 1 upon 4 sine 3 theta, right? Okay. Now we got this function Okay, so we have this type of the function, right? Wave function, and these are in terms of eigenfunction we can write. Now we can express this wave function f of x equal to a sine cube pi x a equal to, okay, equal to a constant, and what is the expansion of this by using this relation? 3 upon 4 sine pi ax, right, minus 1 upon 4 sine 3 pi a into x, right? So this is a wave function. Okay, this is a wave function. Okay, still we have not written this in terms of eigenfunctions. Okay, first of all, normalize this. Normalize this wave function. That means from 0 to a mod of psi square dx equal to 1. Okay, take the simply a square of this wave function. Okay, so all terms are real. So we can write this. We can take a 4 common, right? We get mod of a square upon 4 in bracket of 9, right, plus 1 equal to 1. Now see here, here I have not solved this whole problem, otherwise this problem will become a lengthy one. Okay, if you have the practice of this, how to use this one, take the square of this and equate this is equal to 1. So here I have used this condition, this property, orthogonality of the eigenfunctions of particle in infinite potential well. This one, they are orthonormal to each other. Okay, so integration with the same function will be 1. That means this is equal to 1 if m is equal to n, and this is equal to 0 if m is not equal to n. Okay, so by using this one we get this answer, right? So mod of a square into 10 upon 4 equal to 1, right? So from this we get mod of a square equal to 4 upon 10, right? So take the square root of this. So what we get? A equal to 2 upon root 10, right? Just a minute, let me check. This is a wave function, right? Square of that, here should be 16, here should be 16, here should be 16, square of that. So we should write 16 upon 10, 16 upon 10, sorry. So it is 4 upon root 10. This is a normalization constant, right? So knowing the normalization constant, rewrite the wave function psi of x equal to 4 upon root 10 in bracket 3 upon 4 plus, into sine of pi ax minus 1 upon 4 sine of 3 pi upon a into x. Okay, now again, if you take the 4 common, psi of x equal to 1 upon root 10, right, in bracket 3 sine of pi ax minus sine of 3 pi a into x, Now adjust these terms in terms of eigenfunctions. We know that eigenfunction is square root of 2 upon a into sine of n pi a into x, right? So if you observe here, n is equal to 1, so it is a ground state wave function, right? And these are second excited states wave function, right? So we can write here, rearrange the terms, wave function is equal to 1 upon root 10 here 3 into, yes, I'm rearranging the terms, root a upon 2 into root 2 upon a. Okay, to adjust these terms, to adjust this, write this function in terms of eigenfunction into sine of pi x minus root a upon 2 into root 2 upon a, right? Into sine of t pi a into x, right? So this wave function can be written like this, 1 upon root 10 equal to. So here again we can take this common, this term common, uh, root a upon 2, right? And in bracket we can write, so this is what, a phi 1 of x, right? Ground state wave function minus, and this is, sorry, 3 should be there, 3 into, this is a phi 1 of x, right? This wave function, and this is a phi 3. So here we should write it is a phi 3 of x, phi 3 of x, right? So we got this. Okay, so what is coefficient of, that means we should write this wave function in terms of n is equal to 1 to infinity cn into phi n, right? That means c1 phi 1, c2 phi 2, and so on. Okay, so after comparing this equation with this, so what we get, x equal to uh, t root 10 into root a upon 2 into phi 1 of x, and minus again 3 root 10 into root a upon 2 into phi 3 of x. So this is coefficient, that means c1 and c3. Okay, so from that, knowing this one, find out expectation value. To find out the expectation value of energy, we have this formula, n is equal to 1 to infinity mod of cn square into en. Okay, so simply taking the square of this and substitute that in this equation. Okay, and write down corresponding energies for E1 and E3. Okay, so here write down E3 in terms of E1. Okay, you will get this answer. So this question is asked for 10 marks. Okay. Now, some problems on, again, infinite. So there are many problems are asked on infinite potential wave. Now see, a particle of mass m is confined in the ground state of one-dimensional potential wave extending from x equal to minus 2l to x is equal to 2l. So width is enlarged now. And wave function of the particle in this state is given by this. Okay, cos. Okay, so this is obviously a ground state wave function, and a is a normalization constant. Now these are the options are given. Normalization constant is this. Now see, now here without evaluating this one, we can guess also what is a normalization constant. Okay, now see, we know what is a eigenfunctions for the particle in infinite potential wave having the width from a to 0 to a. Okay, so this is the eigenfunction, right? Now From this, width is what? How much? Is from width is from minus 2a to L, sorry, minus 2L to plus 2L. So width is what? How much? It is 4L. So everywhere replace A by 4L. So we will get the answer. So in this case, amplitude, okay, this constant is A. Is replaced, if you replace A by 4L, 4L. So what we get? We get simply a 1 upon 2L. Right? So this is the answer. This is the answer. And what is the corresponding eigenvalue? So this is a ground state wave function, cos. Okay, so actually this is the symmetric wave potential. So first ground state wave function is this cos. So for that, again energy En is equal to h cross square pi square 2m, and here is a square n square. So for ground state n is equal to 1. So this is 1, right? 1, and replace this a by 4l. So what we get? If you replace this a by 4l, we get h cross square pi square 2m, and here instead of a substitute 4l bracket square. So we get En is equal to h cross square pi square, square of the 4 is 16, and 16 to the is 32, right? So it is a 32 m l square. So we get this answer, option A and option C. And last one is what? Expectation value. Expectation value of energy. Now see how to find out expectation value of energy. Sorry, expectation value of momentum, p square. See, so no need to evaluate the integral. So expectation value of p square, we can evaluate like this: E equal to p square upon 2m equal to h cross square pi square upon 2m. Okay, what we got here energy 32 m l square, right? So expectation value of p square is simply just multiply by 2m here, 2m into h cross square pi square 32 m l square, right? So here m get cancelled, it is 16 only, right? 16 only, but here it is given 8. Okay, so option A and C is correct. Okay, now take this next problem. This problem is asked in January 2014. If a dagger and A are creation and annihilation operators for a linear harmonic oscillator, then which of the following is are a Hermitian operator? Now see, before that, we should know what is the definition of Hermitian operator. We know Hermitian operator is if A dagger equal to A. That means what is the definition of the A dagger means what? It's transpose and complex conjugate, right? It is a what we call adjoint. Right. Now, for that, take A is equal to this first operator. A into A dagger plus A dagger A. And take if this satisfy this condition, okay, if A dagger of this we get the same, then we can say this is a Hermitian. So take the A dagger both side of this. So what we get? A into A dagger A, A dagger A into this. Okay, so we can split up this like this: A into A dagger of this plus A dagger A of A dagger. Okay, now here we are going to use one more property: AB dagger equal to B dagger A dagger. So this is a fundamental property. Now So you use that property here. So what we get? A dagger is equal to a dagger of dagger, a dagger plus a dagger into a dagger of a dagger. Right. Again, dagger of dagger is a again into a dagger plus a dagger into a. Right. So what we get? We get the same a. Right. This a. So this is a Hermitian. This is the Hermitian operator. Right. Okay. Similarly, check for the next one for B. So now let a dagger minus a dagger a take the adjoint shape adjoint of both sides. Oh, sorry, adjoint of both sides. What do we get? A into a dagger minus a dagger a. Again, split up this a dagger minus a dagger a and use this property again. So what we get? A into a dagger minus a dagger into a. Right? Okay. So we got the a again. Right? We got the a again. This. So again, we can say yes, this is the Hermitian. Now let us move the next C. Now for this, again take A equal to I a dagger minus A. So A dagger of this I a dagger minus a dagger of this bracket. So a dagger complex conjugate. So it is a minus 1, right? Minus I, right? In bracket a dagger minus a dagger of that. So what we get again here? We will get minus I. A dagger of a is again a minus a dagger, right? Okay. Now if you take this minus sign inside the bracket, so what we get? What we get? We get I a dagger minus a, right? Again we got a, right? So again third one is also a Hermitian. Okay. But now what about the third one? Third one is let a equal to I a dagger plus a. Take the a dagger of this I a dagger plus a for a dagger. So what we get here? Minus I into a dagger of a is a only. Okay, and plus a dagger, right? If you observe, so we do not get the a again, right? We do not get the a again. Okay, so therefore their answer is all a b c are the Hermitian except this operator, right? Okay. Now let us move to the next problem. Particle moving from minus infinity along the x-axis. Particle is moving from this direction with a total energy E approaches to the x equal to 0, where it is subjected to the potential P for a time t tends to infinity. The probability density P of x is schematically shown in the figure below. Okay. So correct shape of potential is. Now see, in this case there are two states are there. One is scattering state and another one is a bound state. So for the scattering state, for scattering state or unbound state, we can say scattering state total energy is greater than the potential. And for bound state, total energy is less than P naught potential. This is a bound state. Now see, now how to plot. So by observing this one, we will find A and B are bound states and C and D are a scattering state. Now for this problem, you should know how to draw a qualitatively wave functions. Okay, for first potential, for first potential, for a bound state. So this is the height of the potential and this is the total energy E. So this is a bound state, right? So in this case, wave is coming from the left side, right? So there is no any potential. So wave function we can write like this: a raised to plus I kx, right? So because of this potential, okay, there is some probability bouncing back. Let's say b e raised to minus I kx, right? Now, because of the wave nature, it transmits through this and again it oscillates. So in between, this wave function is like this, say c e raised to minus kx only. Okay, it is not oscillating. That's why I have not written I over here. Okay, so it is oscillating in this region, say region first. Okay, and it is exponentially decaying here. So minus kx. And again, it is oscillating here, but it is going in a one way. So here we should write a d e raised to say plus I. Sorry, here should write a k. Suppose say it is k1, k2, and k3x. Right? So in this case, so these are wave functions. These are the wave functions, oscillatory wave functions, right? So if you take a probability p of x in region first, so what do you get? Ultimately, we will get a oscillatory function, addition mod of this. That means wave. Sorry, what is the wave function in a first region? Is a e raised to plus I k1x plus b e raised to minus I k1x. Right? If you take the mod of this, okay, if you take the mod of this, it is again oscillatory. Okay, if you take the complex conjugate of this, psi star psi, so again it is again oscillatory because of this part, right? Now, so this probability is not constant because see, in this problem, in region first, this probability is oscillating, but in this region, probability is constant. Okay, so I have to choose in which region the mod of x is constant. Now, again, in second case, b. In second case, for bound state, e, and this is phi naught. Again, we will move from this side, okay, and it will reflect back also. Okay, so same way we can write here a e raised to plus I k x e raised to minus I k x. Amplitude is different one. In this case, because of the bound state, what we can say, wave function is not oscillatory. Wave function is not oscillated. It will decay like this. Okay, so in this case, wave function will be some c e raised to minus k. Suppose it is a k1, and is a k2, right? So in this case, if this is the wave function, c into e raised to minus k2x, right? Again, if you take the mod of this, it will not vanish in this region also, in this region also. Okay, we will get something, this function. But now, in case C, is a V naught, and this is a total energy E. So in this case, we will move like this. So there is some probability of reflection. But in this case, as this is a scattering state, wavelength will be increased. Okay, and particle has some, suppose here we write A e raised to some plus ikx. Here we write psi 2 is equal to some B e raised to minus ikx. And here we can write it is C e raised to plus I k2x. Right? If you take mod of this function, so what we get? Simply we get a mod of c square. Mod of c square. Okay, because complex conjugate this will be a 0 and we get a mod of c square only. Okay, so this is a constant. Okay, this is a constant. Okay, so we got this answer. But now see, in this case, for scattering state, for this case, E. So particle will move like this. There is some probability of reflection, but here again there is oscillatory solution in between. So wave will move in this direction also. There is some boundary for reflection, right? So in this region, and wave will be move in this direction. Okay, so what we can say, probability will be constant in this region only, but in this region, first region and second region, the probability mod of psi square is oscillatory. Okay, but in this region is a constant. But what is given to us after this, it is a constant. So here we can say the option is C. Okay, mod of psi square is constant there. Okay, I think I have tried to cover the most of the problems. Shashi sir.
Yes, sir. Yes, sir. It's very
Ha,
fine.
ha,
But if you can
ha,
give certain tips to the students, that
ha.
will be better.
Tips.
So,
Ha, tips is
what are
ha.
the topics we should give more attention? The technical problems, what type of problems we have discussed. Related to that, if certain tips are given, then it will be easier for students for preparation.
Yes, sir. For
Please.
undergraduate students, they have asked very basic problems. Most of the problems, as I observed from the old question paper, is from infinite potential wells, sir. Most of the problem is related with the infinite potential wells, then the de Broglie hypothesis, and some the requirement of wave functions, like that only. Hardly, I think there are in a given single question paper, hardly there are 3 or 4 questions are there. Hardly maximum.
Not
Okay.
not
For
that
under,
much. 2 or 3 questions,
yes, yes, sir.
but very basic and conceptual questions are there. Very little calculations are also required.
Yes, sir. Yes, sir. Yes, sir. So
Okay.
there are some nice books are there for quantum mechanics. Introduction to Quantum Mechanics by David Griffith, DJ Griffith, and another one is Quantum Mechanics Concept and Application by Jet Li. Okay, so Jet Li's book is very nicely written books for the undergraduate students. So student can most of the so there are so many problems are solved problems are there in that book. Jet Li's book.
Apart from that, any e-content like YouTube's or something?
E-content. Yes, sir. There are some YouTube,
Not many
NPTEL.
sources are there.
Yeah, sir. Some Swayam portal where some videos are also available on YouTube's also, sir.
Even your Wikipedia also gives a very nice information related to all these
Yes,
topics.
sir. Yes, sir.
So students should go for that too. that e-content or the Wikipedia or websites like that. There are lot of content
Yes, sir. Yes, sir.
available.
So student must learn from the undergraduate syllabus. Students should go in depth. They have to use a different reference books because from the single textbooks now they will not get enough information necessary for this exam.
If we can start your camera.
My
If it
camera
is
is
possible,
on, sir.
your image is not seen on the screen.
Means okay, screen is not visible, sir.
No.
I request
Yes, sir.
to
Yes, sir.
share your all the solutions on your on our WhatsApp group,
Uh,
please, in PDF
I
format.
will share. Okay, sir. Yes, sir. Yes, sir. I will share all the solutions on the
Yes, sir. Please,
group
please.
also.
Thank you so much.
Yes. Yes, sir. Yes, sir.
okay. Is there any query? Any student want to ask anything about quantum mechanics and the related problems? Please raise your hand. Okay.
Okay, sir.
So, shall we go for the vote of thanks?
Yes, sir, please.
Yeah. Okay, all dear students and teacher members participated today. You have seen the huge experience, the experience shown by himself, Dr. Gorakshanath Gote sir. I think he is teaching physics, this quantum physics from last 20-25 years. So the ease of solving problem, the whatever the conceptual understanding and how to solve the problems that easily he has shown with his example. So IIPT SRC 08C and Central IIPT is very thankful and grateful to him for sparing his time with our students and demonstrating his problem solving skills. So that easiness will help our students at the best. So I congratulate him and I'm expressing my gratitude towards him and all the participants and teacher members. So we have completed fourth session today on one of the topic, very important topic of our NGP examination, that is quantum mechanics. Apart from that, there are several other topics, but because of the very few number of resource persons are available, and because of the paucity of time too, uh, we are not able to cover all the issues here. Doesn't matter, but this is one of the very nice event and nice effort by Dr. Gote sir to demonstrate his skills and the content of this particular session, what he delivered. So once again, I'm thankful to all and the Central IIPT for providing this particular platform. Dr. Shinde sir, Shashikant Shinde sir for our active part in this organization and student members to be a part of this particular series. So thank you all once again and good night to all. So we'll
Yes, sir.
stop the session today here.
Yes, sir. Thank you, sir.
Thank you.
Mhm.
Yeah.
Okay, sir. Thank you.
Shinde sir, let's stop the.
Yes, sir. Please, everyone leave the meeting. I'm just going to close the meeting. Thank you so much.
Yes.